Most people see this problem and immediately get lost in ranges, overlaps, and greedy chaos. They try to simulate everything, and it completely breaks. But here's the truth. This problem is secretly a DP plus interval merging masterpiece. And once you see the pattern, it feels unfairly easy. Let's break it down. Today we are solving LeetCode 3661. Maximum walls destroyed by robots. You have robots placed on a number line. Each robot can destroy walls within a certain distance range. Find the maximum number of unique walls destroyed. Inputs: robots, I position. Distance, how far it can reach. Walls, J positions of walls. Each robot creates an interval. Position, distance. Position plus distance. But here's the catch. Robots can overlap. Walls must be counted only once. This is not just greedy. It's about choosing how intervals overlap optimally. Let's take a simple example. Robots equals 2, 6. Distance equals 2, 2. Walls equals 1, 2, 3, 4, 5, 6, 7. Step 1. Build intervals. Robot 1 position 2 dist2. Range as 0, 4. Robot 2 position 6 dist2. Range 4, 8. Key question: what about wall at position 4? Both robots can destroy it, so we must decide who takes overlapping walls, how to maximize total count. This is not independent decisions. Each robot affects the next, so we need sequential decision-making, DP, brute force approach. Try all combinations of robots. Assign walls to robots. Avoid double counting. Exponential, impossible for large inputs. We process robots in sorted order. Why? Because overlap only happens between neighbors. Core strategy: between two robots, we divide walls into 3 regions. 1. Left only. 2. Overlap. 3. Right only. So for each pair, we calculate left walls only current robot can destroy. Right walls only next robot can destroy. Both overlapping walls. This leads to DP. We maintain 2 states. Avail max walls if overlap not used. Used max walls if overlap is used. Let that sink in. Pre-processing. A equals sorted. Zip. Robots. Distance. Walls dot sort. A. I equals. Position. Distance. Walls sorted for binary search. Helper function. Def count LR. If L greater than R, return 0. Return bisect underscore right, walls, R. Bisect underscore left, walls, L. Returns number of walls in L, R. DP states. We track 2 states. Avail equals 0 hashtag walls we can still freely assign. Used equals hashtag walls already committed, fixed. Think. Avail. Flexible. Can still choose assignment. Used. Locked in result. Initialization. Used equals count. A0, 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 1. A0, A0, 1. First robot only covers left side. Main loop. We process robot I and robot I plus 1 together. For I in range N. L. DL equals A, I, R. DR equals A, I plus 1. Define coverage zones. Robot I covers right. L1 equals L plus 1. R1 equals min. L plus DL. R1. Robot I plus 1 covers left. L2 equals max. R. DR. L plus 1. R2 equals R1. Count walls. Left equals count. L1. R1. Right equals count. L2. R2. Both equals left plus right count. Overlap. Both equals walls that can be covered by either robot. Transition. Core logic. Case 1. Keep flexibility. Navail equals max. Avail plus left. Used. Either extend flexible walls. Avail plus left. Or fallback to committed used. Case 2. commit walls. Used equals max. Avail plus both, used plus right. Either. Use overlap optimally. Avail plus both. Or extend committed. Used plus right. Update. Avail used equals navail used. Final step, same position walls. 4x in set x for x, underscore in a. Used plus equals count, x, x. Add walls exactly at robot positions. Return. Return used. Code breakdown. 1. Sorting. A equals sorted. Zip. Robots. Distance. Process robots left right. 2. Count function. Count, LR. Binary search count walls in range. O log n. 3. Core regions. L1 are 1 current robot exclusive. L2 are 2 next robot exclusive. 4. Overlap. Both equals left plus right, overlap. Classic inclusion exclusion. 5. DP transitions. Navail equals max. Avail plus left, used. Used equals max. Avail plus both, used plus right. Interpretation. Avail we haven't used overlap yet. Used we already used overlap. 6. Final add. Used plus equals count, x, x. Add walls exactly at robot positions. Common bugs. Off by 1 in ranges. Forgetting overlap subtraction. Not sorting robots. Pause here and try visualizing intervals yourself. This is one of those problems where drawing helps a lot. If you understood this, you're already above 90% of candidates. What interviewer is testing? Can you convert geometry intervals? Can you handle overlaps cleanly? Can you use DP on sequences? What to say in interview? I process robots in sorted order and use DP to decide how overlapping walls are assigned. That sounds level-headed. Follow-ups. What if robots were 2D? What if walls had weights? What if distances changed dynamically? Let's recap. Convert robots intervals. Break into left/overlap/right. Use DP to resolve conflicts. The real insight is, when decisions affect neighbors, think DP. This problem isn't just hard, it's a pattern unlock. If this clicked, drop a like in the comments. Try resolving without code. And ask yourself, where else can I apply interval plus DP? I'll see you in the next one.